So thank you, the organizers, for this invitation to talk to you here. If I told teenager me 15 years ago that I would be giving a talk to high school teachers, he would be absolutely terrified. So here we go. So just to tell a little bit about my story, I did my undergrad in Brazil, in Florianopolis, a little island in the south. Moved for my PhD in Durham in the UK, and now I'm doing a joint postdoc between Minnesota and Perimeter Institute. So in terms of weather, it's great to be here, enjoying the spring, running away from the Canadian winter. So in this talk, I want to tell you a little bit about the ideas that people have been thinking about for physics beyond the standard model. What were you searching for and what were you likely to find in what directions? So the idea is that towards the end, we're going to look into a few headlines that you can expect to hear if we are successful in the endeavors that we are pursuing. So I just want to start by saying that physics is a very large field, growing field for the matter, and that there are several directions that one can choose to study. Some of them may also blend in and give us information about particle physics, but that in this talk, I'll be talking about high energy probes of very small stuff. And what that means is that we're using high energies to probe very small wavelengths. So you probably know by now that the energy of a particle is inversely proportional to the wavelength of that particle when we think about it in terms of waves. So for example, the energy of a photon is given by this expression where h is Planck's constant and c is the speed of light. Okay, so if we go to high energies like we do in particle physics, we probe small things. What small things? Well, this is the standard model that you've stared at for the whole morning and early afternoon. So you're already familiar with the particles involved. And I just want to point out that one of the fathers of the standard model itself, when they first introduced the model, had very humble words to say about their work. Of course, our model has too many arbitrary features for these predictions to be taken seriously. And yet, it is the most successful particle physics theory that we currently have. But it's not good enough. It doesn't explain a lot of different features. We cannot accommodate the fact that neutrinos have masses in the standard model. We cannot explain the existence of dark matter in our universe. We cannot also explain why we are here. Why are there more matter than antimatter particles in the universe? I also just want to say that the standard model is painted with some tools, with a brush, a paintbrush. And this paintbrush is quantum field theory. This theory is a tool that can be used in particle physics or condensed matter or any other field. And it's the language in which we write down the fields of the standard model, the elements and the interactions between the particles. So Anthony Z, in his very famous book, Quantum Field Theory in a Nutshell, who has an office here, tells us towards the end of the book, quantum field theory can arguably be regarded as the pinnacle of human thought. And yet, towards the end as well, he says it is not complete. So there's work to do both in understanding the fundamental blocks of the universe, as well as in understanding the tools that we use to describe it. So with that in mind, let me jump to particle physics itself. So this is the Large Hadron Collider that you're probably familiar with. We have CMS on the left, and here Atlas on the right. And the idea is that the protons go around this ring, get accelerated to very high energies, and collide in the centers of these detectors, producing lots of new particles. Just to give you an idea of the scale of these experiments, this is a huge effort with a huge number of people. So Atlas and CMS have each above almost 5,000 members. So this is truly an international and huge collaboration. And triumphantly, almost 10 years ago now, they were able to find the Higgs boson. So here is just an example of an event where the Higgs is produced in proton-proton collisions in the middle of this mess that you see here. But because it's so heavy, it decays very fast, and its decay products are then detected coming out of this mass that you see in the middle. So these are 4 muons coming from the decay of the Higgs. So this was the last piece that we were missing in the standard model. We now detected it. We have been checking that its properties indeed look like the Higgs that we wanted, that we had in the standard model theory. And so far, it does. It looks like the standard model we were looking for, which is in a sense a little bit disappointing. So did we find anything else? Now here, let's not be scared by the long list of measurements here, but I just want to give you a sense of how many different measurements, different channels we can look at to look for new particles in new physics. Each one of these lines is a given final state, a given analysis, a given search for outcoming particles from that center of the collision. And each bar here tells you something about where the new particle that would induce that reaction is not. So we have not found this new particle all the way up to this large mass of 7 TeV. We have not found that other particle all the way up to that mass, and so on and so forth. So this tells you that we've done a lot of work as a community, but we have not really found anything beyond the standard model Higgs. So where else can we look? And this is a question that more and more particle physicists are asking themselves. Away from the collider setting, where can we look to find something beyond the Higgs? And to understand that, I just want to tell you a little brief story about how particles interact in the standard model. So particles interact by exchanging force mediators. And these mediators come with a given coupling strength. This is how much the particle interacts with each other, with what strength they interact. And it also comes with the mass of the mediator inversely proportional to that. So if the mediator if the force mediator is too heavy, the interaction between the two particles that are exchanging that mediator is very small. If the mediator is light, that interaction will be stronger. And if the coupling is large, then that interaction will also be larger. So on the right here, I think someone at lunch told me they didn't understand weak interactions. So maybe this helps a little. We have the neutron, which is made up of up and down quarks, here glued together. It's undergoing a decay, where the time is going upwards here. It's undergoing a decay process through the W mediator, which is a force carrier, producing a proton, an electron, and a neutrino. The W is the mediator of the weak force, one of the mediators of the weak force. And you can see that the W carries charge. So you go from one particle that has zero charge, zero electric charge, to something that has a positive charge and the electron. And the W is carrying some of the charge away from the quarks into the lepton sector here. So the one thing to note about this process is that it's very rare. It's a very weak interaction. And that's very strange because the coupling of the weak force, this factor G, is actually larger than the coupling of electrons through photon exchange. So the weak interactions are actually more strongly coupled than electrons through electroweak interactions. But what the difference is that in the case of the W boson, it is a very massive mediator. So the interactions, the exchange between these bosons is very costly. So you pay a large price to interact through this mediator. So it's because of the W mass, excuse me, that this interaction is very weak. Okay, now that we understand that concept, I'm plotting the coupling of the new interaction here on the y-axis and the mass of the mediator on the x-axis. So this mass is given in terms of, in units of proton mass. So the proton would live here, and these are the weak bosons, the W and the Z, as well as the Higgs boson up here. In the standard model, we have some particles here at the bottom that I'm putting according to their masses. You can see the weak mediators and the 3 leptons. You can see that they're pretty different in mass, and that the neutrinos, which are almost massless, are all the way to the left of this graph. So one of the open questions in particle physics is actually to explain why are the particles distributed on this axis so differently. Why is the neutrino so much far below here in mass compared to the electron and the tau? But the other story here is that the standard model lives up here with large coupling strengths. And we've been trying with the LHC to explore what's beyond at large masses for particles that are even heavier than the Higgs, the W, and the Z boson. But the other alternative is to explore particles that may be lighter, but have much smaller coupling strengths. And this is called the intensity frontier. And we have some particle that I can produce in the laboratory, but I just don't observe because it's not produced very often. Its coupling G is very small. So I need to produce a lot of new particles, have a lot of interactions before I can produce one of these new states and then claim a discovery. So that's the intensity frontier. And like I said, the typical mediators here have an interaction strength of G over M. So I'm pushing on this diagonal line down here. And that's where we're hoping we may find physics beyond the standard model. So maybe it's not here to the right at large energies, but it may be here down in the diagonal and low couplings and low masses. Okay. Any questions so far? No. So let me tell you a little bit about what we can possibly find in the next 10 to 20 years. And these will be biased and optimistic predictions from my part. So I'll ask my colleagues to excuse me for a few minutes. And I will start with a word of caution, which is that life is hard. As a scientist, if we're claiming for a new discovery that could fundamentally change the way we see nature and understand the interactions and components of the universe, that's a pretty big deal. And it's probably a good idea to apply the ACRI standard. Here, Carl Sagan puts very eloquently, extraordinary claims require extraordinary evidence. And that's why we're here. That's why we have workshops like the one in KITP, where we get together, forget about the problems that we have and try to focus on a solution to this vastness of data and the difficulty to try and fit it all together. So the first one, to be or not to be, neutrinos had the answers all along. So you can expect, if everything goes according to plan, an answer to this question around 2030 to 2035. This question has to do with the fact that we exist and that matter, let's say an electron, is more abundant than antimatter in the case of the positron. The symmetry that takes you from a matter particle to an antimatter particle is called the charge parity symmetry, CP for short. And since we're here, we haven't been annihilated away by antimatter, we know the symmetry should be broken. In a sense, that's like my two cats, pretty similar, but something has to tell them apart. And please don't tell that to my partner, but this crazy one here is my favorite. So I have preferential treatment for him. In the same way, the universe would have a preferential treatment for matter over antimatter. And in the case of neutrinos, there's something very curious that happens. The oscillations that we hear about, and we heard throughout the morning, they can happen differently between neutrinos and antineutrinos. So this oscillation wave that we're measuring can look different whether I run my experiment in neutrino mode with a neutrino beam, or in antineutrino mode with an antineutrino beam. And this would explain and would tell you what parameters in the neutrino theory can tell you about the preferential treatment of nature to matter over antimatter. So experiments that will be doing this include Dune, which we heard a lot about today. So one small piece of information that may be interesting is that the Dune beam is actually pointing downwards. So to go from Fermilab in Illinois to Sanford Underground Research Facility in South Dakota, the beam actually has to point downwards because otherwise you just come out the horizon. So next time you have a flat earther with you, you can tell them this is the most expensive way to prove that the Earth is round. The other experiment is Hyper-Kamiokande in Japan. So as we heard, it's a huge tank of water. For perspective, the tank is as tall as one of the towers in Tower Bridge in London. And it will be seeing neutrinos inside of this tank after they interact inside of the water, and Cherenkov radiation is emitted and detected in these photon detectors. So these two experiments together can tell us what parameter would enter into the birth of the universe that would give matter a preferential treatment over antimatter, and therefore explain why we're here. It's a pretty big deal. But on to the next topic. This may be a little bit of a controversial one for my colleagues, but I decided to put this in. So new evidence for ground unification of all forces. Physicists see proton decay. So prediction for that, later than 2030, but maybe never. It just may be that the proton is stable. So why do we believe that this is an interesting thing to look at? So we know that heavier particles like the muon, the tau, may decay to lighter particles, emitting energy in the process. So once you realize that the proton is actually a pretty heavy particle, 1,000 times heavier than the electron, you should ask yourself, why is it that the proton doesn't just decay back to electrons and quarks, here in the case of a pi zero? The answer to this question is not known, but effectively we can phrase it in the following sense. Particles can carry what's called a quantum number. This is a number that describes the particle by a given quantity. And in this case of the proton is a baryon. And baryons carry baryon number equals 1 in the case of the proton. The final states that I'm allowed to produce in proton decay, they carry baryon number equals 0. So if baryon number is a conserved number in nature, you do not expect protons to decay. Unless I can find another baryon in which the proton can transform into, protons will remain stable. This is a pretty big deal. If we find the baryon number is violated in our theories, we find something fundamentally new. So far, all we've known is baryon number conservation. And to give you an idea of why we're doing this, well, the answer is very simple. When we have an experiment like Hyper-Kamiokande with this huge volume full of protons, we can ask, out of those 10 to the 35 protons, which is a huge number, if a single one of them decays into a positron plus pi zero, that would be seen by this experiment as flashes of light, looking like exactly reconstructing the mass of the proton. So this is a pretty incredible signature. We have not seen this so far. So in this plot, I have the lifetime of the proton on the x-axis. And on the y-axis, I have a couple of different channels, decay modes that the proton can undergo, which have been looked for, but not found so far. So at the very top, in this case, if the proton goes to positron plus pi zero, you have lots of experiments setting limits. And a limit here means that for example, for Kamiokande, the proton lifetime has to be above a given number in years. So you see here the super K number, which is the current best limit in this mode here, and you see the advance of hyper K, which is going to tell us that the proton has to be at least as long-lived as more than 10 to the 35 years, which is a pretty long lifetime, much longer than the age of the universe. So this is a very sensitive probe, which tells you that it's sensitive to something that can be very weak, an interaction or a new effect that is very small. And one way to think about this is that what's happening to protons when they decay in some new theory is something that is coming from a new particle and much heavier scales than anything we've probed so far. So on this plot, we have time after Big Bang, or another way to think about it is energy. And here we are at low energies. But if I go to higher and higher energies, I know already that the weak force and the electromagnetic force combine into a single one. I also hope that the strong force and this electroweak force would also combine into one grand unifying interaction. This unifying interaction would be able to decay the proton through this diagram. Now time flows to the right, and you see that it transforms the two up quarks inside of the proton into this new particle X, some new force carrier related to this large scale grand unifying force, into the positron and the down quark, producing the pi0 meson. So if we observe proton decay, it would be one of the highest scales that we have ever probed in particle physics, and it'll be a pretty big deal. It can have consequences for the unification of all forces that we know of. It will tell us the baryon number is not a conserved number in the theory and in nature. Okay. The third one is this new particle could make up 85% of matter in our universe. So this is about the discovery of dark matter. It may happen, likely to be found at some point, but we cannot rule out the possibility that we'll never see it. It's purely invisible particle out there. I should also explain to you why it's 85% of the matter when people in the morning have been telling you that it's 25, 27%. I'm not lying. I'm just making a distinction between matter, which constitutes normal matter, and dark energy, which don't ask me about, has nothing to do with normal matter. And out of the known matter that we have, dark matter is pretty dominant. So we know dark matter exists. Here's a photo of our galaxy, an artistic impression. Here's where we live, somewhere in one of these arms of the galaxy, which is basically a disk. And around this disk, there will be a big puffy and inert halo of new particles that actually bound the whole galaxy together. This new puffy thing is something that interacts gravitationally with each other and with us, but may or may not interact with us through some another force. On the left, there's quite an interesting example of why an evidence for dark matter. And what you're staring at are two clusters of galaxies that have collided with each other. In red, you see ordinary matter. That's coming from X-rays. And in blue, you see this new dark matter, this inert matter, which is not observed. We haven't seen it with telescopes or some interaction. This is through the gravitational lensing. So the light that is coming behind these clusters gets bent by the gravity of this volume, and that's how we know that there's mass there. So the fact that there is mass in blue, which has been unaffected by this collision, and that the mass that we know that we can see in red has been affected by the collision slowed down. Tells us that dark matter was there, and it's some inert gravitationally interacting particle. Okay, so we have a lot of guesses for what dark matter could be. Here's just a pretty picture of our visible world inside of this bubble: electrons, muons, UNI, quarks. And outside of this visible world, there are hundreds of possibilities of what dark matter could be. In terms of a fundamental particle description, dark matter could be a particle called the axion, which is some light, fuzzy-like particle that could be permeating the whole space. It could be a form of a dark neutron, some particle that looks like the neutron, but it doesn't interact with our forces. And it could be something like a WIMP, which stands for weakly interacting massive particle. And what this WIMP is something that looks like the W or the Z boson, or a heavy version of the proton, and interacts with us in this energy scale around the electroweak scale, which is the mass of W and Z bosons. This has been the main candidate for a very long time, and there are several experiments looking for that. And the way they do so is by having some volume of a gas or a bunch of nuclei inside of a very quiet place. And in this environment, because it's so quiet, any disturbance to the nuclei inside of this volume would be observed by the detector. So in this case, what you're hoping for is that this local population of dark matter, which is inside of this puffy halo in the galaxy, one of these particles will come and interact with the nucleus inside of this volume, which will jiggle the nucleus a little and produce light that becomes observable. So this would be one way to detect dark matter. And if we do so, it will be a pretty big deal as well, because we'll find something in this 25% of the universe or 85% of the matter. Okay, this fourth one is pretty interesting, something pretty recent as well. So physicists find a fifth force in nature in the mysterious wiggle of the muon. What do I mean by that? And the prediction here would be, if we have done our calculations right, which is a big if, probably by the end of this decade, we'll have seen this headline. So muons are just heavier cousins of the electrons. Like we discussed before, because it's more massive, it can decay back down to positrons, in this case, and to neutrinos through the weak force. But before they decay, they behave like an electron. They have an electric charge. And just like any other particle, they also have a quantum spin, which is, in this case, since they're fermions, spin a half. So through this analogy of spin as a rotation around a given axis, S, this particle can interact with a magnetic field, which, depending on that direction of the magnetic field, causes a precession of this spin. What happens here is there's a quantity, which is an inherent property of the muon, that tells you how strongly this muon interacts with this magnetic field, and how does that precession around the magnetic field axis look like. So this quantity is described by this prefactor G, where here you see this magnetic dipole moment mu of the muon is described by the charge of the muon, the mass of the muon, and its spin. And G is a number that in quantum mechanics is very close to 2, except for very small corrections coming from quantum effects. These quantum effects are what we're trying to compute. It just so happens that the G in the muon can be computed very precisely and can be measured very precisely. That allows you to probe not only your tools to compute this quantity, but also new effects that may be coming in and leaking into this quantity from a new sector, a new physics particle. On the left, I have a bunch of diagrams that are telling you that through photon exchanges between the muon and these other particles, I can cause a correction, a contribution to that number G. And I'm showing you all of these diagrams to basically show off that in quantum electrodynamics, which is our best description of electromagnetism, you can compute this thing to 10th order in a small coupling. So what you do is you have a leading contribution and you expand, like in a Taylor expansion of a function in terms of a small parameter. And we go all the way up to the 10th order in that small parameter in the case of electromagnetism. So people have computed this number very precisely. This is an incredible feat of the field, but it's not the only contribution to that number. There's also a contribution coming from the electroweak force, the W and the Z bosons. This is also very well known. It can be computed very accurately. And there's a final one coming from quantum chromodynamics, or the strong force. This one is much harder. And you can see here, there's a bunch of stuff happening where these little springs here are actually gluon exchanges between the particles. That's the mediator of the strong force. And what happens in this case is that the gluons interact too strongly. So your perturbation theory, which you could do really well in the case of electric dynamics, breaks down and the effects get out of control. We have ways to fix that, and we have data to try and compute this more precisely. But the story I'm trying to convey is that pieces of this calculation are very well known. For example, QED and electroweak sector. And other pieces we think we have control over, but we're working very hard to make sure that that's the case. And you can see that all three forces contribute to this number. This is a pretty amazing observable. You're sensitive to electromagnetism, electroweak forces, and QCD, quantum chromodynamics. So this is the number. It's a very, because we compute it so accurately, you need a lot of numbers after the decimal point. And you can see the theory estimate, which comes from QED, electroweak, and a lot of other contributions here that I'm not going to really get into the details, does not match the experimental number. It matches at the first, second, third, and so on digits, but the disagreement really happens at the 11th digit after the decimal point, which is a pretty amazing feat to even say that we can reach that level of precision. So the question is, are we missing a new quantum correction from a new force in this parameter? And that could be. And the good news is, if we have a new force, which we'll say is mediated by a particle called the Z prime, so something that looks like the standard model Z boson, but is slightly different, that would carry its own coupling strength, and you would carry its own mass. So there's a coupling strength and a mass that are unknown. But I know that the correction to that number that I'm measuring here, the difference between the standard model prediction and the experiment would have to obey this formula here. The main lesson is that this formula goes like coupling over mass. Again, the interaction strength of these new mediators usually goes like a coupling over a mass. So if I invert this and I ask, this should match exactly the discrepancy that I see between experiment and theory, I get a result that the mass of this new particle cannot be much larger than 100 times the mass of the proton. This coupling could be small, this coupling can be large, in which case it would be around the mass of the proton, but it can also be small, in which case that mass can be much lighter. So it's all the way up to 100 times the mass of the proton or lighter, depending on what this coupling G is. So that's pretty good news. We have access to this scale of 100 times the proton mass. That's something that we can produce at the LHC. So we can try and look for this force directly. And you would look for this in the muon sector. You look for this by producing muons and looking for a new interaction between them, or a new particle that decays to muon pairs, and things like that. So we hope to observe this either at the LHC directly by producing these particles, or even at neutrino experiments, which, as we saw this morning, produce a lot of muon-flavored neutrinos. So if we have something wrong with the muon sector, you would also expect something weird going on in the muon neutrino sector. Okay, so this also a pretty big deal. It would mean that muons are fundamentally different from electrons, and there is something that tells apart the different generations of leptons in the standard model. Okay, and the final one is depth of a nearby star makes neutrino detectors light up around the world. So pretty self-explanatory. Can happen any day now. Hopefully it waits a little bit longer until we have the bigger detectors. But the idea is that a star undergoes supernova, and the sheer number of neutrinos that it emits is detected throughout all the different neutrino detectors we have on Earth. So for this is a plug for George's talk that is upcoming next. So you can learn more about it then. Okay, so to summarize, we talked about news about CP violation, or why is there more matter than antimatter? We talked about evidence for ground unification through proton decay. So this will be a pretty big deal. Maybe all forces in nature are just one at the super high scales, super high energies. We also talked about finding out what is this particle that makes up 85% of matter in the universe. And finally, we discussed this mysterious wiggle of the muon, which is something that we have seen hints of in the recent years. And maybe something is going wrong, but we haven't seen what this new particle that would be contributing to that number in a weird way. We haven't seen that particle yet. And finally, the depth of a nearby star, that would be as exciting as it gets for neutrino astronomy. So with that, I'll thank you, and I'll ask my colleagues that are hiding at the very back if they have any additional comments or things that I may have missed that you're excited about. Thank you.
Thank you, Matheus, for the journey into potential future discoveries.
Right.
If any of these things happen, you can say you heard it first. So we're very excited about this. And any questions? All right.
Thanks, Matteo. So question, it sounds like the detection systems for dark matter are super similar to the detection systems for neutrinos, like big underground tanks full of liquid that light up from interactions. And it also sort of sounds like neutrinos have many of the same attributes as dark matter in terms of their lack of interaction with any electromagnetic field.
Absolutely. Yeah.
So is it possible that neutrinos themselves could be the dark matter we seek?
Yes, so that's the first question that every grad student asks themselves in the first particle physics course. So that's a great point. Unfortunately, standard model neutrinos, as we know them, with the very light mass that they have, do not have enough mass and enough density to explain what we see. They're also too fast. Because they're so light, they travel too fast with a lot of momentum. So they wouldn't look like what dark matter looks like, which is more of a slow moving inert fluid. You could have new species of neutrinos that don't have the weak interactions. They're called weak stereoneutrinos. And those, if they're heavier, not too heavy, but just heavy enough above the mass of the neutrinos, but below the mass of an electron, which is still pretty light, relatively speaking, but much heavier than the standard model neutrinos, then they could explain dark matter, but we haven't seen them yet. So yeah, short answer is there's not enough mass in the neutrino sector to explain the full vastness of what dark matter is. Although you could argue that neutrinos are part of dark matter, just nowhere near enough to explain the full amount that we see.
So two questions. One about the Z prime. We have a lot of LHC data already. Could we search the current LHC data for Z prime, or do we need higher energy or more luminosity?
Yeah, we can, and people have. This is a very large field. So this Z prime can look like many different things. It can couple only to muons, or it can couple to muons and taus, or it can couple to all families. And depending on what it does, it will give you a different final state, a different channel to look at in the LHC. So there are several searches. Many of those will be shown in that long list that I showed at the beginning. But so far, no luck. Nothing conclusive yet that we have seen some new force carrier. But that's something that people will be doing. With the LHC, the future of a high luminosity LHC, which just means you're shooting even more protons at each other, you're getting even more collisions. This would be nicer because if this Z prime couples very weakly, in the sense that it doesn't interact very strongly with the standard model, you may be producing more of them, and it may be easier to detect them. Yeah.
All right, second question about the equation with the G over M and the strength of the interaction. I think that photons and gluons don't have mass, so how does that work?
I was waiting for someone to catch that. That's a great question. So that is only valid when the mass of the particle involved in the interaction is larger than the typical energy scales involved in the process. For photons and gluons, the gluon case is a little bit more complicated because they're strongly interacting. The theory doesn't behave in a very simple way that we used to think about in terms of Feynman diagrams, what you're seeing here. In the case of the photon, interaction just goes like the coupling strength. And in that case, it's the electromagnetic charge, 0.3, numerically speaking. In the case of the gluon, it's more complicated because you cannot write down these diagrams. You have collective effects, and these things are more complicated to describe, but their interaction will be proportional to a alpha S, which is the, or GS, you can imagine, the coupling strength of the strong interaction.
Okay. So with this, the fifth muonic force, so I'm trying to understand what they would be fundamentally different from electrons. And then again, I apologize if I didn't catch this. Where does that leave the tau? And then the other question, can I ask the other question?
Yeah, of course.
Okay, so is this, if we do this, then you kind of said that the proton decay would indicate grand unified theory or unification of the force. And then, so I guess I'm not following where that would, what's happening with the proton that would link gravity into the rest of them.
Okay, that's two great questions. So the first one was, what happens to the taus if this thing is there? And we don't know. This new force can couple only to muons, and it would explain why we haven't seen that in the electron sector or in the quark sector. And that's just the way it is. We have to come up with a theory. And why is this new force preferentially talking to the muon sector? We don't know. But it could also talk only to the second and third generations, the muons and the taus. And that's actually a theory that a lot of people work with. And it's something that conserves the total number called L mu minus L tau, which is muon number minus tau number. Turns out that that combination is a special combination that looks really good in your theory. There avoids some problems on the theoretical side. And it gives you something that does not talk to the first generation, but talks to the second and third. The significance of having that new conservation law and that new mediator is beyond me. I think we would have to think harder about what that means in our fundamental theory of interactions. But it would have to fit somewhere. It will tell you something that the muons and taus are special in some sense. So about proton decay, which is separate from this, so independent of whether there is this new particle or not. What that's telling you is that there is something that happens, sorry, where is it? Of very high energies that has a very small indirect effect at the low energies that is transforming the proton and carrying this baryonic charge through this new particle here, breaking this conservation law of baryon number. We don't know that that would imply grand unification. It is not the sense that if you see proton decay, you can deduce that all forces are unified. It would be a very strong indication that there is such a thing as grand unification. The reason for that is that all of the couplings between the three different forces, so let's ignore gravity for the moment. The three fundamental forces carry their own coupling strengths. GS, electric charge, well, there are subtleties, but there are three couplings, and those couplings are energy dependent. If you probe them at the low energies, they have separate values. And as you go to higher and higher energies, because of quantum corrections, quantum mechanical effects, these couplings vary. And it just so happens that they start converging to a single value. In the standard model, if you compute where that happens in energy, turns out these lines don't cross each other all at the same point, which would be a very nice thing to say, maybe they're all converging to this new unified force. But there is some region where they're close to each other, and that makes people think that there would be such grand unified force. And a lot of these theories predict proton decay. So it would be a great coincidence if you observed proton decay, and that your best theories that unify all of these interactions were also predicting proton decay. But one doesn't, these grand unified theories imply proton decay, and we're testing it, but proton decay doesn't imply that we have grand unified theories. So for gravity, we just don't know, because we don't know, we don't have a theory for gravitational interactions. We identify the three interactions, yes. Maybe this diagram is too optimistic. Yeah. No, we don't have a fundamental theory for gravitational interactions at the large scale, right? That's quantum gravity. We don't know what that looks like.
Hi. The 86% that is matter, normal matter, is that the entire 86% of the entire pie, or 86% of the 27 and the 5%?
Oh, I just mean that dark matter, this 27%,
yes,
is 85% of this cut of the pie. I just mean that 27 divided by 27 plus 5 is 85%. So okay, out of the matter, which constitutes normal and dark matter is 85% of that.
I see. Okay. All right. Thank you.
I'm just trying to emphasize, we know nothing about dark energy. So sometimes I find it a little bit misleading to put it all in the same graph, because we just really don't know what this is.
I'm sorry. So the 85% is of the entire pie. So the 15% is dark energy, or?
No. So if I forget about dark energy, then I have a universe made of matter and normal matter. 85% of that is dark matter. So, yeah.
I don't know if this is a relevant question at all, but we've talked in the talks today, we've talked about, say, the Z prime particle having a larger mass. What about the particle sizes of all these particles compared to the particle size of an electron in terms of dimensions? How does it even matter? Or
you mean the physical size?
Yeah, the physical size and the relationship to, I think there's some kind of a constant, Planck constant about a limitation on the physical size.
Yes, those are all.
I do not know if the question is irrelevant, but it's just a thought that went across that.
No, of course. So here we started by understanding that energy is inversely proportional to the wavelength of this wave-like particle. But we also know that energy is, in some sense, equivalent to mass. So the mass of a particle is also inversely proportional to its wavelength. So the more and more massive this particle would be, the smaller its wavelength. So if we say this particle is much, much smaller than the electron, usually what that means in quantum mechanics is that it's much heavier than the electron. I don't know if that answers the question. Yeah.
I'm not sure if we could answer this question, but in detecting neutrinos to kind of serve as evidence for dark matter being that halo around our disk of a Milky Way, can that detection tell us if this dark matter is like rotating in the same way as our disk is rotating, or is that even a thing that can be detected?
So the detection of the neutrinos is a separate thing from the detection of the dark matter. The experiments may look similar. The same experiments may do both, but these are separate things. So the neutrinos we're trying to study to understand the neutrino sector and possibly new physics. But the dark matter is, we're trying to look for this new thing that is in the halo everywhere, kicking these nuclei or normal particles inside of our volume. If you detect something, and let's say you have several of these new events, then you can start learning about what are their masses, what are their typical velocities, and that will tell you something about the properties of dark matter. But the distribution of this halo around the galaxy is really a more of an astronomical question. These particle detectors are probing the particle nature and the fundamental properties of this new particle. So I don't see how the dark matter detection in these lab experiments will tell you something about the distribution of this halo. You'd know something about it because you can see the typical velocities of them, and that feeds into the typical distributions of these particles in the galaxy. But it wouldn't be a direct probe of that.
Any other questions? If not, let's thank Matheus again.
Thank you.